SwayamPrabha. Digital India. Educated India.
This is one of the most important lecture in classical control, which is root-locus method. So root-locus method basically the graphical technique for designing and analyzing the control system. Here we will see how the locus of the poles or the roots of the system going to change with the varying controller gain. We'll have some rules through which we'll be designing the root locus plot. And from the plot, we'll see how the locus is going to start from poles of the system and ends at zeros of the transfer function. So it is basically will be varying the controller gain from 0 to infinity, and we'll see the range of the controller gain for which the system will be stable. And also we'll be finding the controller gain for which the system will be marginally stable. And from that marginal value of the controller gain, we'll be designing the PID controller using Ziegler's-Nichols rules. So in next few lectures, we'll be spending on this particular topic, and we'll see how we can design the closed loop control system using root locus method. In this lecture, we'll be discussing one new topic on control system design. From the last lecture, we have discussed that how the system stability can be analyzed based on the controller gains. So how the controller gains is going to be effective, and based on the range of gains, we can comment on the stability based on the controller gains. We can comment on the stability, and this technique this part we have discussed through the concept of Routh stability criterion. Basically, the range of K's or the gains on which the system will be stable. This part we have discussed. And in today's lecture, we'll be coming up one new concept, which is the concept root locus. In this concept or technique, we'll be discussing how the system poles going to change with the change with gains. So how the systems poles and zeros going to behave with the change in the system parameter. If you say the parameter is the gain, so how the system poles going to behave on the S plane? This is my S plane. This is the imaginary of S and real of S. So how this poles going to change on this S plane with the change with gains? And these changing poles, it is called locus. How the locus of the poles or zeros going to be effective with the change in controller gains. So let's work on this part. This is quite interesting, and this part will be dealing next few lectures. And the concept, this technique, will be using for the autopilot design of the translation and rotational motion of the aircraft. So let's start. Let's consider the following closed loop system. The following closed loop system. This is, we are having the reference signal R, and we are having the controller gain K, and the plant, let's assume we are having GS, and we are having the output from this Y, and this is error, this is the feedback from the output terminal, this is negative, this is positive. And another important concept in this technique is we can take the open loop system and we can check the stability of the closed loop system. That is another important takeaway from this concept. We will be discussing later very soon. The closed loop transfer function from this figure 1, the closed loop transfer function, we can write Ys divided by Rs equal to K into Gs 1 plus K Gs. In this block diagram, we'll be checking how the system poles and zeros going to be effective with the change with the gain K. We'll take this controller gain as the only parameter going to be changed, but later we'll extend how we can twin the PID controller gains. That is another important topic we'll be connecting through this technique. Now the characteristic equation from this closed loop transfer function, we can write 1 plus K Gs equal to 0. So this is basically, if you solve this equation, we'll get the poles of the closed loop system. Roots are the poles of closed loop system. Now, if you assume or if you write Gs can be one transfer function where we have numerator polynomial and denominator polynomial. Then equation, let me write, this is equation 1, for example. Then equation 1 can be written as we can write 1 plus K into ns ds equal to 0, where let's assume K is greater than 0, for example. And from this, we can further write ds plus kns equal to 0. And from this equation number 2, if we assume, let's assume n be the order of ds. So here n, we are assuming here the order of ds, and we are assuming M be the order of ns, the maximum power of s, n be the maximum power of polynomial ds, and m be the maximum power of s in numerator polynomial. So now we can write, if you notice this equation number 2 very carefully, if k tends to 0, we can say ds goes to 0. So it means very, very important concept it is. This is the concept we will be using in root locus. Poles of GS, if we assume n poles, that because the order of the polynomial is n poles, and we are assuming there are n branches, and if k, so n branches means how the each pole on the root locus going to vary with k, and if k tends to infinity, we can write, if it is k tends to infinity in this equation, we can write ns equal to 0. So it means we can write zeros of GS, where it is basically m zeros, right? M zeros. So if you notice very carefully, if we consider k tends to 0 or k equal to 0, the root locus starting from poles, where we can solve this equation ds, because from this equation number 2, if k equal to 0, ds equal to 0, so we'll get the poles of this equation of this polynomial. So as we increase k, it goes to zeros, because from this equation we'll get the zeros. We'll start from poles and we'll end at zeros. So let me write, each branches starts at pole of GS and approaches to 0 of GS at k tends to infinity. Now we'll extend this concept for our attitude control system of the aircraft. Then you can get the better idea how it is happening. So let's consider our aircraft PD controlled attitude system. So if you remember, we had the transfer function ys by rs equal to kp divided by I, and we had the polynomial for denominator s square plus kd by I into s plus kp by I. So this is the expression we had. And the characteristic polynomial from this transfer function, we can write the characteristic polynomial, we can write s square plus kd by I into s plus kp by I equal to 0. So this is the polynomial, and here we'll be checking how the root locus is going to be. We can design the root locus for this particular characteristic equation. Now to make our lives simple, let's assume We are assuming the inertia of the aircraft system for one axis, if it is theta phi side. So if it is one axis, we are assuming 1 kg per meter square. And we are also assuming kd equal to 1 to make our things simplify. Based on this assumption, the equation number 3, let me define this equation number 3. Equation number 3, we can write s squared plus s plus kp equal to 0. So in this equation, we will check with the change of kp, how the poles going to vary. So if you find the roots of this equation, we can write s equal to s1 to there is 2 roots minus half plus minus root over 1 minus 4 kp divided by 2. Now, let's look the poles S1 and S2, how it is going to vary for the different values of Kp. So when Kp varies from 0, Kp will be 1 by 4. We can write the closed loop poles are real and lie between -1 and 0. So if you have these values, you will have two poles, which will be one pole, another will be 0. So let's look. Sorry, there is a typo in here. 1 by 4. So if you take Kp 1 by 4, then there will be two poles which will vary between 0 and -1. Now, if you draw these poles in our S-plane, if you draw them in S-plane, so there will be two poles, one is at 0, s equal to 0, and another pole is s equal to -1. And when Kp equal to 1 by 4, there are two repeated poles at s equal to -half. And in this case, if you notice carefully, if you plot them at the same point, there will be two repeated poles. So let's assume this is -1. So we can write here there will be two repeated poles, s equal to -half. And so if you notice carefully, with the change of Kp, the poles are shifting on S-plane. So now, if you assume Kp is greater than 1 by 4, the roots are imaginary. So how? So if Kp is greater than 1 by 4, we have two poles which are -half plus minus j 4 Kp -half. And in this case, a real part is -half. So let me draw the in S-plane how these poles are evolved. So here real part is -half, and there are two complex conjugate part of these poles. One is here, another one is here. So here, this is, we can write root over 4 Kp -half, and this is another part 4 Kp -half. This is negative. And again, if you combine all the condition in one spline, let's look. If you combine all of the above locus, we can write or we can draw in a spline. So initially with the condition of this condition, there are two poles which are 0 and -1. So there are two poles, one is 0, one is -1. And if you take the another condition, this condition, in this condition, the pole locus come to here, which is -2. So it means the locus is coming like this with the changing of k, and at -half it become imaginary. So we can say, and here it become complex. So we can say at this point the breakaway happens and the poles goes to like this. This is how we can draw the locus of S. This is a very important concept from this. So with the change of gain, the locus is changing. It's going another direction. And this point actually breakaway happens. So we'll be discussing in detail how we can find these breakaway points and where these poles are going. So this is how the locus being created with the change of controller gain. So from this discussion, let's have the note. At is equal to half the root locus or Lucy sometime we call on the real axis mate, and then split the complex split to the complex plane. That what I have noticed here in this in the above S plane, and this the point at which the split happens is called breakaway. It is also observed that, second point, the root locus shows how the closed loop folds change in the S plane with the change in parameter. Here parameter is k. So with the parameter, changing parameter in the system. And third point we can write from this change in parameter, we can the controller design concept. And this part is very, very important. So this technique will be using very frequently for the autopilot design of the different motions of the aircraft. Now we'll be coming up some rules how we can draw the root locus. If you follow those steps, we can easily come up with this root locus. This is very, very important concept in control system. So let me write down these rules. Rules for constructing the locus. First, let's go with the closed loop system, and let me write the open loop transfer function from the closed loop system. We have summing point here. This figure is very, very important, and we are frequently using this figure because this is the closed loop control system and how the autopilot being developed based on this closed loop control system concept. This is our controller block, GC of S, which gives the output U of S to the plant GP of S, and from the GP of S we are getting the output Y of S, and we are assuming unity feedback system minus plus, and this is we are assuming the R of S is the step some reference signal, and CLTF we can find TS. Let me define this, the transfer function, closed loop transfer function of this figure 2, and the transfer function Y of RS we can write GP of S, GC of S 1 plus GP of S, GC of S. The characteristic equation we can write 1 plus GP of S, GC of S equal to 0. And the OLTF we can denote in the following structure. So here basically this is what I have done during the steady state analysis. This is we denote as a open loop transfer function. G naught S we can write in the structure GP of S, GC of S. We can write as K is the controller gain, system gain. We can write S minus Z1, S minus Z2 dot dot S minus Zm, and we can write in terms of folds S minus P1, S minus P2 dot 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 S minus Pn. This is basically gives the open loop zeros, and this gives open loop poles. So if you notice here, we are going to consider this open loop transfer function, and we are going to study the stability of the closed loop system. That is the beautiful thing in root locus. We will be considering the open loop transfer function, and we will see the behavior of the system in the closed loop sense. So let's have the list of rules what you can follow to come up with the root locus plot. So rules. I think this part we can continue from the next lecture because there are 6-7 rules we need to discuss. We'll continue from the next lecture, and we'll also coming up some example how we can come up with the root locus plot based on those rules. Let's stop it here. Here we'll continue from the next lecture.